Hello everybody, Thy Lord Root here, and welcome to a series of tutorials for KSP that I decided to throw together. And so, I thought we would start out by doing a sandbox mode game, and I believe that this is actually for new players the best thing to do. You can do the training, of course, to help get you acclimated, but I think it's probably good that we start out in sandbox, and there's a number of reasons for that. If we go here to the sandbox game, you'll notice that it says we are free to play without any constraints. And so in this case we won't be doing any science or anything like that, but we will have access to all the rocket parts, and we will have virtually unlimited funding. This compares to science mode, which we must use to unlock technologies by doing science. This is what the career mode was like up until 0.24. And then there's career mode, which adds funds. And in addition to that, you have to unlock your buildings as well. So let's just call this tutorial sandbox. You can go here and you can select your mission flag. I'm just going to leave it as the default for now. I think that that's an okay way to start out. So the goal for this episode is to explore rockets, and in particular exploring how to get into orbit. And that will be somewhat important, because getting into orbit is perhaps one of the hardest things for new players to do. So a word of advice here, this building here we won't be able to go to because we have no funds. Same for the contracts building, or not the contracts, but administration building over here. And for the science facility as well. So by clicking on the VAB, that's that building in the center, we come to this building here, and you can see we have a bunch of parts. Let's just start out with a very basic rocket. And let's think about what a rocket needs. A rocket, of course, needs a command pod. This is where you control the rocket, and you have the option of either manned or unmanned pods. So here we have this command pod Mark 1, which is kind of like the Mercury pod, and that's good for a variety of reasons. We also happen to have these probe cores here, which will allow us to do things like satellites and space probes. Another thing we might want to do as well is put an engine on this thing. I'm going to put an SRB in for that. Now there's two kinds of engines. You have this SRB, which has the fuel included, as you can tell, but you can't throttle it. In fact, once you turn it on, you can't turn it off. And so these tend to be good for your liftoff stages, because they don't have very good we call it specific impulse. You can see the specific impulse doesn't get any greater than 240. When you have an engine, specific impulse rather can be important, in the sense that this tells you how much mileage you get out of your fuel. It's kind of like the miles per gallon in your car, and that is that's very useful to know. You want usually a high specific impulse if you can hack it, but in some cases, like when you're launching, for instance, you want more thrust than specific impulse. So that's something to keep in mind. And then, in addition to that, we have another thing we want to put on, which is, of course, a parachute. Because if we don't have the parachute, what will happen is that we will leave a smoldering crater in the ground where the spacecraft has crashed, and generally you don't want that. Now over here you can see we have this staging diagram, and I want to point this out because in a design like this, this SRB will go off at the same time as the parachute. And that can be quite bad because the parachute will of course slow down the SRB. And so what we can do is we can hit this plus button down here, create a new stage as I've just done, and then you can drag this little icon here down to the proper place. And that is pretty much where we want to be. So I want to point out as well that one of the things in 0.90 we have now is we have craft stats. You can see we have 3 parts in it. The height is a little bit over 4 meters, and we have a width of 1.3 meters. It's actually 1.25, but I believe it only rounds that off to the first decimal place. So that's something to consider as well. This becomes more important in career mode, where you do have limitations on how many parts you can put in a rocket and how much weight the launch pad can support. And in fact, let's talk about that a little bit. What does it take to get off the ground? Well, what it takes in particular is that we have a thrust to weight ratio of at least 1. And what is thrust to weight ratio? Well, the thrust to weight ratio is essentially the amount of thrust that comes out of this rocket compared to the weight. And if it's below 1, we're not going to be able to get off the launch pad simply because we can't overcome gravity. So the easiest way for us to figure that out is to take into account the weight of this capsule. Now, we have a weight, or a mass of 4.7 tons. However, the trouble is that we have to factor in gravity, because mass is the same irrespective of where you measure it. And so, in this case, we have 4.7 tons as a unit of mass. Those of us who are used to the imperial system also recognize the ton as a measurement of weight, and that can get a little bit confusing. But if we multiply this by 10, then what we'll find out is that this has a weight of 47 tons. And why multiply it by 10? Well, if we multiply it by 10, what we'll end up doing is we'll end up factoring in Kerbin's gravitational influence, which I believe is 9.81. That's the gravitational factor on here, gravitational acceleration, rather. And if you've taken a physics class, then you may know Newton's second law, which is force equals mass times acceleration. And that becomes important here. So we have a thrust on this SRB of 250 kilonewtons. And in this case, we have 47 kilonewtons for this entire vessel. That mass will incidentally go down if we drain all of the fuel out of this by right-clicking on the SRB. And then look at the info. We can see that we have a final weight of 1.4 tons. So we're good for the most part. The question is, will this get us out of the atmosphere? And the answer is probably not. You see, we don't have enough delta V to do that. Delta V is the amount of change in velocity that your engine can affect. And that can be a bit, that becomes important. Basically, the more delta V you have, the longer you can burn your engine. Anyway, let's go ahead and press T for stability. You can see a bunch of really cool things come up here, like, for instance, we have this thing that points us prograde. We're going to keep it on stability assist right now. That'll keep us pointing at our current heading. And I'm just going to hit space to launch this thing. This basically fires the first stage. So we're actually moving at quite a speed here. This is not terribly efficient. In fact, we are very likely to move past terminal velocity. And on a body with an atmosphere, terminal velocity is a thing to consider, because with terminal velocity, that's basically your speed limit. In fact, when we hit about 300 meters per second, we will hit the speed of sound as well. You can already begin to see we've got shock waves forming off of our vessel. That's a neat little atmospheric effect, but unlike in real life, it's nothing you really have to worry about. The shock heating is not a huge issue here. And so this gets us up to maybe about 15 kilometers or so. You can see we're rapidly losing speed, and that is due to drag. You see, the atmosphere, as we well know, is not nothingness. There are particles in it, and when those particles hit the spacecraft, it slows it down ever so slowly. So, yeah, we'll just reach the top of our orbit here. If we hit M, we can actually see that. We're very close. This is a point called our apoapsis. And the apoapsis is basically the highest point in your orbit, or in this case, because we're on a ballistic trajectory, meaning that that orbit is a parabola, the height of that parabola. And so you can see, in fact, that this is very slowly going down, this apoapsis, and we're about to reach it in 2 seconds as well. So there we go. You can see when we come down that we have this velocity indicator, and that velocity indicator gives us an idea whether or not we're moving towards or away from the ground. Here we're moving at close to 100 meters per second. I also want to point out that we're pointing towards retrograde right now. And what retrograde is retrograde is the direction opposite of the direction your rocket's traveling. This is something that I think that confuses people just a little bit, because your rocket can actually be traveling in a direction that it's not pointing at. And I think that's something that does maybe mess with people a little bit. Anyway, if we move away from this, you can see retrograde has a cross in the center, and it has these little lines pointing out of it. There is another direction, if we point straight down, called prograde, and prograde is the direction of our travel. And so this gives us a velocity vector. Our velocity is basically in the direction of prograde with this speed here, this 273 or 274 meters per second. So we're moving relatively quickly in comparison to speeds on Earth. This is like 400 miles per hour. An easy rule of thumb, if you are confused about this, is if you want to get miles per hour, you simply multiply it by 2. That's a good rule of thumb. Anyway, at some point we have to start thinking about popping our parachutes. And we could do it now, in fact. this will do two things. It'll slow us down, and then it'll also get us pointing, in this case, towards our retrograde vector. And as you can see, we are very slowly moving towards that. Now, the reason we aren't exactly on it yet is because of the fact that there's Newton's first law, that an object that's in motion remains in motion. And so that parachute is actually applying a force that causes us to rotate just a little bit. Anyhow, you can see that we're almost down here. And if you hit this period key, the one that has the less than, or the greater than symbol on it rather, you can speed time up a little bit. You want to be careful with this when you're landing, for the very reason that if you're not careful, what'll happen is that you will, you'll end up ripping your parachutes off. That happened to me recently, and I lost my pilot because of that. The pilot in this case is a guy by the name of Jebediah Kerman. He is a guy you'll probably see a lot of, unless you do contracts to rescue Kerbals or something like that. So anyhow, let's think about designing an orbital vessel that, oh, you can see too, we landed a little bit too hard there as well. That does cause some issues there. If we land faster than about 6 meters per second, then we can lose parts of our vessel, which you generally don't want to do. Another thing we can do while we're out here is we can hit that EVA button and we can jump off, take a little bit of a walk, and we may not be able to do that here. Actually, yeah, we can take an EVA report down here. We're not going to get science from it because we're in sandbox mode. We got that, and then we can take a surface sample as well. So there we go. We can just move back towards this guy. Hit F to grab. Hit F again to board. And then if we move our, if we move our mouse up here, we can recover the vessel. Well, so much for that. Now, this rocket got us part of the way, but not nearly as far as we would have wanted to. And so let's think about another design here. Let's think about a craft that has staging on it. And so the idea here is that if we go to structural, or we could even go over here to the advanced mode, if we go to filter by module and go to decouplers, then we get these guys here. This basically separates the part below it, so when we fire, or when we stage this decoupler, what'll happen is this guy will remain on the stage that we're discarding. Let's put a small one there. Let's put a fuel tank there, and go to engines. Get this LV909. This guy, when we fire the decoupler, will move away like that. The decoupler will remain attached to it. Now, if we look at this, we have 26 tons, or 26 thousand, or 26 kilonewtons rather, is what I meant to say. And this engine has a thrust of 50. So we are well within our limits there. And we have a higher ISP, so this guy will last a while. And there are some things to point out as well. If we go over to filter by module, we have deployable solar panels. We can take these guys here, and we could stick them on. If you hit X, you get symmetry mode, which can be very useful. I'm just going to put, oh, I don't know, maybe 8 of those guys on there so that we'll always hit the sign. That becomes very important in space, by the way. If you lose power in space, you can't control your vessel, which is not so good. But, you'll notice that, in principle, we should have added about 0.04 tons in mass. And that might actually have been the case. But if you look here, we've changed a little bit. These are actually massless parts, so it would appear as though this craft stats deal does not take that into consideration. These basically do not contribute to mass whatsoever. Now, some of these guys over here, like this guy that has a mass of 0.4, will actually contribute to it. So it's good to know what parts are massless. There are other ones to think about, like for instance, if we go down to maybe the data transmitter, most of these are massless parts. What about power? RTGs are not massless, if I remember correctly. However, these lights are. And if we go down to, where is it? That's animate generic. Those are parts with animations. Some of the batteries are massless as well, if I can find them. If not, then we'll just leave those be for the time being. So we do have a positive thrust to weight ratio here. We could even put more fuel on this if we want to. Now I do want to say something about liquid fuel, in fact, that if we go to filter by function, we have these tanks that are very slight gradations. So I like to consider this sort of the canonical 1.25 meter tank. And this has a mass of about 2.25 tons with 180 units of liquid fuel and 220 units of oxidizer. This guy right here is about half that, and this guy is a quarter. This guy, of course, is double. Let's go put on another decoupler real quick so that we can mess around with that some. And let's make ourselves a rocket that can get into orbit. What we can do is we can take these FLT 800 tanks. I'm going to put, I don't know, maybe 3 of them on there. That's good enough for the time being. And that gives us 16 tons. Now if we go to this engine here, we have a thrust of 200. This will give us, compared to this actually has 215. The differences between these engines are that, compared to this engine, this does not have an alternator, which means it won't generate power. That becomes important, but not right now. But B, we have gimbaling. on the second engine, which will allow us to more easily control our rocket. So, these cost the same, or this costs a little bit more, but this offers the advantage that you can gimbal your rocket as well. So let's take this out to the launch pad. In fact, we can save this and probably should. We'll call this Test Launcher 1, or TL1 for short. And this will get us a fair amount to orbit. If we take away this guy here, let me just reroute the part. Oh, we're still rooted there. There we go. But if we take this guy away, then you can see it has a mass that is hidden. I'm guessing it's around maybe 15 tons or so, and we can get, with this one engine here, we can get up to 21.5 off the ground. So that kind of gives us the limit here. That also determines, that's not the only limit, of course, there's also the limit of delta V. Let me just go here and reroute this part. I'm doing this basically by clicking that last button there and now clicking the command pod. We are still crewed, so that's a good thing. If we take Jeb out to launch, I think it's good to point out that there is more than one way to approach orbit, or that we might approach orbit, and I think most people are going to be tempted to take this guy and go straight up like this. So let's try that. Oh, we have a staging malfunction. Let me just fix that real quick. That's something that you will have to get used to, as it turns out. Let's just move this guy into a stage of its own. And below that, we will put this engine here. There we go. Staging malfunctions do happen in KSP. It's good to pay attention if you can. I usually do pay attention, but there's a, there's a thing going on with the, to where, I guess because I'm talking while I'm designing, I'm forgetting. Anyway, let's get this guy up and going. You can see we're a lot more loaded now, and that is a bit of a problem. Well, maybe. I mean, we're actually moving at a decent pace. Normally, in Kerbin's atmosphere, a thrust-to-weight ratio of 2 is usually your target. With the mod that I normally play in, or that I have been playing in lately, Ferrum Aerospace, that's actually way too high, but in KSP that's okay, in stock KSP. So let's try going straight up the naive way to get into orbit. And I think, in fact, we're not really going anywhere. So I'm going to kick up time acceleration. You don't usually want to do this because you'll lose control really quickly. But, when you do that, you will find that it does make things a little bit faster. And by the way, there are two kinds of time acceleration. There's physical time acceleration, which we can do while we're firing our engines. And there is also a rails acceleration as well. And you can see we're getting pretty high here. The space starts at 70 kilometers or so, a little bit under 70, but 70 is a good rule of thumb. That's when the music starts. And we have expended that stage. Now, are we in orbit? Well, we have a very, very high parabolic trajectory. And we can keep on going. Orbital velocity on Kerbin is about 2.2 kilometers per second. And we might think, at least in vain, that we might be able to reach that. As you can see, all we're really doing is increasing our apoapsis height. In fact, if it were not for the fact that we were rotating and that we had a bit of orbital velocity to begin with, and you can see here we're getting very close to orbital velocity. And fairly soon, right about now, we're above it. We still are not in orbit. We're just in a very, very high trajectory here. In fact, what could end up happening if we have enough delta V, though it seems unlikely, as you can imagine, we would have enough energy to where we would escape the Kerbin system. Because, as you can imagine, when you get up here, your orbital velocity is way, like, let's take a look at this. You can see our orbital velocity is decreasing quite rapidly. So if we knew what we were doing, we could point our engines towards prograde here, or even fire them east, which is probably a wiser decision. And that would get us pointing the direction we want to go. However, you can see we've spent about a day in space and haven't really gotten anything out of it. In fact, we're landing remarkably close to the KSC. Well, maybe. Not at all, actually. You see, the planet's rotated underneath us by at least once over in a quarter or a third of a turn. You can see we're coming in very, very fast here. And so it might do us good to deploy our parachutes. This is a very harsh re-entry, by the way. If this were real, Jeb would have either been burned to a crisp, or the G-forces would have been too great for him to handle. Incidentally, the human body does have an interesting limit on G-forces. It was thought at one time that you couldn't go above 15 or 20 Gs. A G being the amount of force equivalent to the Earth's gravitation. John Stapp, back in the 60s, I believe, actually managed to hit a limit of 45 and survived. But that must have meant he was also a very hardcore person. Anyway, there are mods if you do want this sort of danger to be present. There are mods for this. In fact, I'm not going to wait for this thing to land. I'm going to revert the flight. But the mod I was thinking of in particular is a mod called Deadly Reentry. So it's clear that we need some horizontal component to our velocity in order for us to reach our goal of orbit. And that is, that's not too hard to do, but we do have to be careful because on Earth we would turn almost immediately. Here, we would actually want to begin turning around 10 kilometers, between 10 and 13, where this sky blue indicator up here on the atmosphere, I'm not sure if you can see that very well, or if you can even see my cursor, but this guy turns into this darker shade of blue. Another thing that would really help is for us to manage our throttle. Now, of course, we don't really have to worry about that too much right now. I mean, we're moving at a pretty good pace. But while you're in the atmosphere, you definitely do not want to be under or over 250 if you can help it, because then you'll start incurring losses due to drag. But in addition to that, you also, really 140 up until the later part of the atmosphere is better. And so the thing is that terminal velocity changes with altitude because the atmosphere becomes less dense the further you get up. And that's important. Now, if we just go ahead and get ready for this, I like to turn a little bit earlier than 10K. Really, you want to turn sooner rather than later, or else your orbit will become very steep. But you don't want to turn too soon either, because you do have that drag to worry about. So, at about 9K or so, I'm going to begin teasing this orbit down. Or in fact, I'll do it the way that most people like to do it when they don't know any better. Most people will then turn down to 45 degrees east. And we will just keep that there. That's not very efficient, because as it turns out, if you have basically this force versus, or the velocity that, the change in velocity that comes from this force compared to the velocity that you already had, then you will find that in this case, not all of your velocity is going to change your speed, or that change in velocity rather. It's kind of confusing to put it that way. But as you can see, on the one hand, we are gaining a fair amount of speed this way. In a way, we're also arresting our prograde as well, though. From ideally, we want it to go to the bottom there. But this may get us into orbit. I hadn't really tested this to make sure. The main thing we want to do now is we have this apoapsis of 136. And about 3 minutes to get to it. Now, to get into orbit, we essentially want to get as close as we can to this. And in fact, while we're doing that, I'm going to do a maneuver node here. If you click on your orbit, as long as it's not intersecting another vessel, which can happen later on in the game, You see this prograde marker here? Well, let's drag it out. You can see that we have a new point coming up called our periapsis. And we want to burn as close to apoapsis as we can. So the point where we reach a circular orbit is where these two are perpendicular to they're perpendicular to the thing, to our present apoapsis. The trouble, of course, is that this takes about 900 meters per second of delta V. We actually started a little bit too late. We should have started about halfway between the start of the burn and the end of the burn. However, it looks like we will get into orbit this way. And we do in fact have plenty of delta V. You can see our periapsis is slowly coming out of the ground. And the periapsis, by the way, there we go. That is not perfect because of the way I timed it. But our periapsis is our lowest point, so we have 113 minus 160. We have plenty of fuel left, so I'm just going to show you how we can correct for that. If we go to our periapsis here, we can now circularize this by moving this guy in just a little bit closer. So that's 113 by 113. That's actually just about perfect. You could see we have an arrow here that points to this maneuver marker. And in fact, we can tell Jeb here to hold the maneuver. That'll be very useful to us. And since we're holding maneuver right now, stability assist is okay to turn on. Anyway, that's a burn of about 1 second at 35.4 meters per second. You can see that we are circular here. So, or not that we're circular, but if we hit this at about the right time, I hit it a little bit early. We're 113 by 112. That's good enough for me. This is a fairly good orbit. And what makes it good is that it's tight. Normally, like if you're just parking, you want to maintain an orbit that's circular. That means that these guys are as close as possible. Really what matters here is the average of these two orbits. This average is probably about, just off the top of my head, I think it's like 113.25 kilometers or whatever. However, let's say that we want to land now. Well, that's not too hard to do either. You'll notice that when we burned retrograde, it decreased our orbit just a little bit. Now, this is actually quite a steep re-entry. It is probably best to burn at about 30k or so. Anywhere between 30 and 40k, that's where the atmosphere will catch up. And if we want to land near KSC, we should probably target that as well. You see, one thing about this, and we just happen to be lucky, because you may have noticed I've been targeting my apoapsis. When you do maneuvers like this, it's best to target them at the apoapsis because, well, in the case of the apoapsis, when you're doing a retrograde burn, that's where the least orbital velocity is. So if you're trying to decrease your orbit, then that's the best place to do it. Conversely, when you're trying to increase your orbit, the best place to do it is at periapsis. Otherwise, you will either waste fuel or, in this case, in this case, you might get a little bit of a radial component that will rotate your deal here. Anyway, I'm going to start burning at about 1 second or so. It's better to burn about halfway through the node, and you'll see this estimated burn time. If we hit Z, that kicks us up to 100%, and if we hit X, that cuts our throttle. And we are now a little bit higher than we want to be, so what we can do is we can tell Jebediah to point prograde, and we can just raise that as desired to 33. There we go. Note that pilots are the only ones that get this. This is a new feature in 0.90 that some people do or do not like. I personally think it makes sense because not everybody can pilot a spacecraft. There's training involved. Anyway, it's possible that we can do two things. Last time, we actually attempted, we jettisoned our main stage or our service module. What we really might want to do instead, in addition to landing at the KSC, is we might want to hold on to this as well. This isn't important in sandbox because you don't have money, but in career mode, you do want to keep on to these things if you can. So let's just get down to the point to where you'll notice after a certain while, about here or so, we will get on down to this point here. I'm going to have Jebediah point in the retrograde direction. Now, why are we pointing retrograde? Well, if we want to land, then chances are we want to land on our engine rather than on our nose cone, right? And so retrograde is the direction we're traveling, or prograde is rather. If we point prograde, then we will unfortunately land on our nose, which is not the best thing to do. Could be quite dangerous, in fact. However, the engine can take a little bit more stress. And so, if we want to land with this thing intact, then landing on our nose is, or not on our nose, but on our, landing on our engine is probably a better bet for us. So I'm just going to speed up time here. We will probably land somewhat short of the KSC, which is okay. We just want to be in the ballpark. I want to stress this habit now because I do eventually plan to do career mode, and it's important that we recover as much as possible. We are just a little bit high on our orbit here. Although it's really hard to say. And we're coming in at a little bit of an angle, it seems. So what I'm going to do is I'm going to slow down a little bit. Although actually, that may not be necessary. We do have plenty of fuel though. There are really two things about this that are worth pointing out. The first is that your vessel will be easier to slow down if it's not fueled, which is part of the reason of staging in the first place, to reduce your vessel's mass. Now, when you're going up, staging has the benefit that what it will do is it will go ahead and, allow you to not have to worry about carrying all your mass up with you, which is important when you're launching. If you can shed weight, then do it. But when we're coming back down, well, remember how force is mass times acceleration, according to Newton's second? As it turns out, by having less mass, we slow down more quickly as a result. Let's see, I'm going to save just a little bit of that for now. We're passing overhead here. Probably going to land in the ocean somewhere. Before too long, we're going to get flame effects. However, because we've slowed down so much, it's not such a big deal. Where we're landing right now is probably a good place to land if you're a beginner. And basically the way that we get to KSC is because the Earth is rotating. Actually, I should be paying attention to this, shouldn't I? I'm just going to go ahead and deploy my parachutes for now, but the Earth is rotating, or Kerbin is, so you want to usually target around here, somewhere between here and here to factor in that rotation. Now, when we get down, and we do want to be careful because anything above 500 meters from the ground, which in this case is sea level, so anything above 500 meters does wreak havoc on the parachutes if you're not careful, like I said. And I'm just going to disable this flight assist or stability assist for the moment so that we can level out. There we go. But you can see we're moving at 8.9 meters per second, which is greater than that 6 meters per second. Now, I could lose this engine if I'm not paying attention. However, because I have fuel, I can reduce that by throttling up just a little bit. And because of this engine's ISP, I can get this guy down to a fairly reasonable landing speed of 5.3 meters per second. And we have now splashed down into the ocean. Well, I just have one more thing to show you, I believe, and that is the best way to approach orbit. Now, we have had this issue to where we, last time we got into orbit, we did so, but we wasted a lot of fuel. And what we can do here instead is when we launch, I'm just going to time warp up to maybe 10 meters per second, or up to 10K here in a bit. But, instead of moving so dramatically away from the prograde marker, which is what we did last time. What we can do instead is we can leverage this rocket's ability to do the heavy lifting for us. So let's just get up to about 9K or so and begin our pitch program. A lot of people like to call that pitch program a gravity turn. Oh, we're a little late. But it's not properly called that, because a gravity turn is when gravity assists you in your turning. And in this case, what we're trying to do is we're trying to tease this guy over. Now, if we, what we can do here is we'll want to keep this guy close to our prograde vector, and we want to keep the time to apoapsis under 2 minutes or so. And now that we're out a little bit more, we are going to go ahead and get as much forward velocity as we can. Once we get high enough, you'll see that our apoapsis is rising, but we don't have much in the way of velocity, so we can actually point this guy below the horizon. And it is about time for us to stage here. And this will flatten out our trajectory. Ideally, we want to get somewhat of an orbit here as we're coming out of the atmosphere. And you can see we're actually quite a bit away from this. And so what I'm basically doing is flattening out this trajectory some. I think somewhere between 80 to 100 is good. And that's not too bad. We now have an orbit around the planet with plenty of delta V to spare. So if we circularize it, we have actually decreased the amount of delta V we need up front, almost by about more than a factor of 9, actually. And that's the important part. So let's get this thing circular. And that only takes us 3 seconds of burn. Now we are using a fair amount of power by doing this way. However, I'm going to burn pretty close to maybe 1.5 seconds. So we'll hit Z about now. And there we go. Orbit is kinda sorta circular. I could probably have done better, but this works for the purposes of demonstration. And we now have a little bit more fuel than we did beforehand. So this is a more efficient way of flying it. Typically, you know, you want to get as much forward velocity as possible. I did not really turn as quickly as I should have, but that's basically the approach. And you can see here that we are now in orbit and Jeb is smiling. One of the things, of course, you'll realize about Jeb is that he likes to smile a whole lot, even when he's in lethal danger. Anyhow, that will do it for today's tutorial, and I may cover orbital maneuvers in the next episode, we'll see. But until then, this has been Thy Lord Root, and I will see you next time.